Okay, so for today, so we will continue our lecture on design lead compensator. So basically, lead compensator is the combination of the lead compensator and lead compensator, same as the PID controller. Okay. So the lesson outcome from this subtopic. So you should able to design a lead compensator that can improve the steady state and the transient response. So if you remember, so to improve the steady state, basically we will use the lead compensator, and to improve the transient, we will apply or we will use the lead compensator. So, if our design requirement need us to improve both transient, and also steady state response, so you need to choose the lead compensator. Okay, so again here, so the objective to use the lead compensator is to improve both transient and steady state response, same as the PID controller. And actually, a lead compensator is the combination of lead and lead compensator that have been learned in the previous topic. And same as the PID controller, so there is two strategies to implement the lead compensator. So the first strategy, we improve the transient, means that we will design the lead first. So after that, we focus on design lead compensator. And for the second strategy, so we improve the steady state error first. So we design lead compensator. So after we design the lead compensator, we'll design the lead compensator. But in our discussion, so we will use the first strategy. So same as the PID controller. So for the PID controller, we will design the PD. So after that, we design the PI controller. So for the lead, so same. So we design the lead compensator first, and then we design the lead compensator. Okay, basically for the lead or lead compensator, same. So you can put it as a lead or lead. Okay, so both name is same. Okay, so the procedure using the first strategy for the lead compensator. So first, we design the lead compensator to meet the transient response. So that's mean you need to choose the Z lead first, and then find the SD compensator, and then from the SD compensator, we can obtain the angle of P lead, and then you can obtain the value of P lead, and then we use the formula to calculate the K using the SD compensator of the lead compensator. So for this value of K, so you need to remember, so we need to include the pole and zero that we obtain from the lead compensator. So after that, we will design the lead compensator to meet the desired steady state error. So how to design the lead compensator first? We will choose P leg. So basically, we will choose the coordinate close to the origin. So maybe you can choose at minus 0.1, at minus 0.01, as long as close to the origin. And then since that the formula to find or to design the lead compensator is given by static error constant nu over static error constant all equal to Z lead over P lead. So the next step, we will find the static error constant of the lead. So it is different from the lead compensator alone. kalau for the LED compensator, so you need to find the K ataupun or static error constant of all. So of all that we refer to the K gain controller. But since this controller is a LED lead, and we already designed the lead compensator first, so our reference now for the static error constant refer to the lead compensator. Faham eh? Boleh eh? Okay, so this is the difference between LED compensator and LED lead compensator here. So for the LED compensator, only for the LED compensator, so what you already learned, so you will find the static error constant, so either Kp or Kv for K gain controller. Okay, so the means that the Kp or Kv all, Kp all or Kv all, so we find from the K gain controller. But when we use the LED lead compensator, so the Kp all and Kv all refer to the static error constant of the lead compensator. Since that we already designed the lead compensator on our first step, so we need to refer the static error constant of the lead. So that's mean either Kp lead or Kv lead. So Kp lead for the step input, and Kv lead for the RAM input. Okay. And then we find the static error constant of the new Kp new and Kv new. So this can be find based on the design requirement. And then we apply the formula to obtain the location of Z-lag. Okay. So after that we can we determine the value of K using the ST compensator. ST compensator of the lead compensator, include the poles and zeros from the lead and LED. So please remember to include the poles and zero from the lead and LED compensator that we have already designed from the first and second method or second step. Okay, and also you can assume, we also can assume that the K of lead LED compensator same with the K of lead compensator. So sometimes you didn't have time to calculate the K for lead compensator. So you just can assume that the value of K lead LED same with the value of K of lead compensator. So basically we can prove that the value from lead LED compensator and K from the only lead compensator is almost same. So we just can assume that the value K is assumed. So you just can take this value on the first step here to become as our K of the lead compensator. Okay. Okay. So from here, so we can conclude that lead compensator has two poles and two zeros. LED pole and zero are designed to improve the steady state error, and the other poles and zero from lead are selected to put design point dominant poles on the root locus in improving the transient response. So basically, from using the root locus method, so we can obtain the transfer function for the LED lead compensator is given by this equation, Ks plus Z lag multiply S plus Z lead over S plus P lag multiply with S plus P lag, since that the lag lead is the combination between lag and lead. Okay, so now we look on the example for the lag lead controller. So so we try to solve or to design the lag lead controller using this example. Okay, given the system of figure below, so you need to design a lag lead compensator so that the system can operate with 20% of overshoot. and a twofold reduction in settling time. Further, the compensated system will exhibit a tenfold improvement in steady-state error for a RAM input. So for lead compensator, choose 0 at -6, and for lag compensator, choose pole at -0.01. And given the dominant poles for the uncompensated system at -1.794 plus G3.505. So from this example, so so we need to design the lag lead compensator. Lag lead compensator. So if you remember, lead compensator is used to improve the transient response. So the first sentence here is the objective to improve the transient response, 20% of overshoot, and a twofold reduction in settling time. Okay, so this is our design objective in order to design the lead compensator. And then the second sentence here further, so the compensated system we exhibit a tenfold improvement in steady state error for a RAM input. So this is the second objective, and we will use the lag compensator to achieve this objective because we want to improve the steady state error. Okay, so another statement. So in this question, they ask you to choose 0. So that means 0 here, lead compensator. So 0 here is refer to the Z lead. Z lead at -6, or we can put it as a Z lead equal to 6. And then for the lag compensator here, so choose pole at -0.01. So that means the P lag is equal to 0.01. Okay, and dia bagi dekat sini adalah uncompensated ST, dominant poles for the uncompensated system. Okay, so the first step, so we will design the lead compensator. So if you remember to start to design the lead compensator, we need to know the ST compensated. Okay. So how to find the ST compensated? So we write the general equation for ST. So any dominant pole is given by minus zeta omega n plus J omega D. So any question? Ada soalan tak? Setakat ni okey?
Okey, Doktor.
Okay. So we will find the ST compensated. So minus zeta omega n plus J omega D. So we need to find the zeta omega n and also the omega D. Okay, and then given here 20% of overshoot. So from the 20% of overshoot, so we can evaluate the value of zeta. Zeta is equal to minus ln 0.2 divided by ln 0.2 power of 2 plus pi power of 2. Okay, and then here, so based on the design statement, it mentioned about twofold reduction in settling time. So from this statement, twofold reduction of in settling time. So we will use the TS. So TS that TS compensator or TS desired is equal to TS uncompensated divided by 2. Okay, so so this is the meaning of this statement, twofold reduction in settling time. Okay, Okay, so to find the TS compensator, so we need first to find the TS uncompensated. So how to find the TS uncompensated? We can obtain from this ST uncompensated. So uncompensated. So the general formula is also given by minus zeta omega n plus j omega d. So from this value, you can evaluate the value of TS uncompensated. So value here is equal to zeta omega n. So we can evaluate the TS uncompensated. So after that, we can calculate the TS compensated or TS new. So same values, TS new or TS compensated divide by 2. And then after that, we from the value of TS new, we can obtain the value of zeta omega n. Same as the PID and lead compensator. And then we obtain the value of omega n. So after that, you can obtain the value of omega d. And finally, we can find the value of ST compensated. So ST new is referred to the ST compensated. So this is our ST desired. Okay, so after that, we find the angle, the angle, the angle. So this is our system. So from the system, so we have here pole at 0, minus 6, and minus 10. Okay, so we have here 0, minus 6, and minus 10. And for the lead compensator, so you need to choose your location of Z lead. Choose. So basically in theoretical, in final exam, so basically we will choose Z lead, same coordinate with one of the location of post, system post. So for this example, so I choose Z lead is at minus 6. So when we choose Z lead, same with the one of post from the system. So we can have the zero pole cancellation, here. So that's why pole and 0 at minus 6. So I didn't draw in this figure. So actually minus 3, you should draw at here, somewhere at here. Sikit lah. Tapi tak ada masalah. Macam ni lah sepatutnya. Should be. Sebab minus 3.58. So dekat sini. Okay, so after that, we find the angle, 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 and angle. So I name it as a theta 1, theta 2, and theta PC. PC, we can put so any place as long because we didn't know yet the exact location of the PLET or PC. So after that, we calculate the value of theta 1. Since that theta 1 here located on the left side of the ST location, so we will apply the tangent, direct tangent formula. And for the theta 2, since that the theta 2 is located on the right side. Okay, so to calculate the theta 2, so you need to include the 180 degree because from the tangent formula, we obtain this angle. Okay, so for the theta 2, so we need to include the 180 degree to obtain the exact value of theta 2. So after that, we apply the formula, summation theta z. So for this figure, we didn't have the theta z, zeros, angle of zeros. So tak payah letak lah. So no need to put the theta z minus theta post. Okay, so we have 3 posts. So we have minus theta PC, minus 47.52, minus 117.13. So equal to minus 180 degree. So you obtain that the theta PC is equal to 15.35 degree. Okay. So since that 15.35 degree less than 90 degree, so the PC should be the symbol of PC should be X symbol. Typing error at here, located on the left side. So to obtain the location of PC or PLAC, so we will use the formula without 180 degree. So you obtain that the value of PC is equal to 29.1. So that's mean we already designed for the lead compensator. G lead is equal to K S plus Z lead. S plus Z lead. So lead Z lead. We already choose that Z lead at minus 6. So that's why when we put it at here, so S plus 6 over, so we already calculate for the P lead here. So it is equal to S plus 29.1. Okay, so after that, we need to find the value of gain K. So apply the formula to obtain the value of gain K. ST here is the ST from the ST new or ST compensated. And for the G, so please remember you need to include the G from the system and also the G from the lead compensator. Okay, since that sepatutnya in this equation, so we have S plus 6 from the lead compensator. From the lead compensator, S plus 6, S plus over S plus 29.1. But from the system, we also have S plus 10, and also S plus 6. So we can cancel S plus 6 for 0 and post. So the equation will become like this. Okay. So after that, we can evaluate the value of gain K. And lastly, we already designed for the lead compensator. Okay. So next, so we design the lead compensator. So from the lead compensator, so we choose the P lead at minus 0.01. Betul ke? Okay, minus 0.01, or in the mathematical equation, so I put as a P lat equal to 0.01. So this is the same meaning that P lat must be at minus 0.01. Okay, first, so we follow the procedure how to design the lag compensator that we already learned previously last week. So the transfer function, and then the formula. So static error constant says that in this question it mentioned about the RAM input. So we will apply the KV because of the RAM input. So KV new over KV lead. So for the lead compensator, so I already changed. So in this note, so we put for the old as a lead. Part dekat sini, the difference between a lead compensator alone with the lead. So for the KV old or static error constant old, so we replace it with the lead. Okay, Z lead over P lead. And then we find the KV lead or KV old. Kalau before this, we find the KV old. So the next step for the lead compensator, we will find the KV lead. So use this formula. So actually, so I need to put something. So dekat sini ada error sikit. So we have, sorry. So ini adalah GS, only for the GS, but for the KV lead, so we need to include the transfer function from the lead compensator. So should be, so we have from the lead compensator S plus 6, 0, S plus 6, and we have here S plus 29.1. Okay, and then we can remove S plus 6, can cancel. So the final equation to find the KV lead is given by this equation. Any tertinggal sikit. Okay, so after that, we can evaluate the value of KV lead. So K here, K here is refer to the value of gain K that we obtain from these values. So we just replace 1977. Okay, any question? Ada soalan tak? Okay, Ashraf okay. Tak ada soalan eh? Ada orang ketat ni yang tak suka ni online.
Okey, doktor.
Okay, awak ni jawab belakang tidur. Okay, so the next step, so after we obtain the KV lead, so we find the KV new, typing error here, since that the input, our input is the RAM input, so you need to find the KV new. Ada typing error, KV new. So from the KV new, so we based on the design requirement. So we want our system exhibit a tenfold improvement in steady state error for a RAM input. So when we translate this design objective into the mathematical equation, so our ESS desired, or I put as a ESS new, is equal to ESS old over 10. So because tenfold improvement, so ESS new equal to ESS old divide by 10. So all here is still refer to the K gain controller. So please don't get confused. So all ESS here is refer to the K gain controller. K gain controller, and so that's mean we need to find the K gain controller first. So using the formula, and ST here is the ST uncompensated given in the question. Okay, so you just calculate, dapat 192.1. And from here, we can obtain the KV uncompensated. KV uncompensated, so replace K with 182.1. And finally, we can find the ESS all. Since that so we use the KV, so the formula is given by 1 over KV. Okay, then from here, we can obtain the value of ESS new. ESS new is given by this statement based on our design objective. So then using the same formula, we can determine the KV new. Okay, and then we apply the formula to choose the P lag to obtain the Z lag. So from the question, we choose the P lag equal to 0.01. So KV new here, KV lead here, and then rearrange the equation so we can obtain the Z lag. And lastly, we can calculate or find the K for the compensated system. Compensated system means for this system include the lead and the lead. So kalau malas gila, if you didn't want to calculate, so you just can put the statement, assume that the K of the lead compensator same with the K of the lead compensator. So we just write the value of K lead. K lead that we already obtained the value of K lead at here. So just tulis je dia sama. So you just can put the value of K is same with the value of K for the lead compensator. Or if we calculate the value of K for the lead compensator, okay, so you need to include. So if you can see here, so this is the transfer function of the lag, and 29.1 here from the lead. So actually, we also have the zeros as plus 6. And for the system, we also have the pole at as plus 6. So because of we cancel these two, so that's why the equation will become like this. And after I apply the formula, so I obtain that the value of gain K is equal to 1,971. So if we observe that the value of K gain here is actually almost same with the value of gain K from the lead compensator. So that's why we just can assume that the K of the lead compensator same with the K of the lead compensator. Okay. And so we already designed the transfer function for the lead compensator. Z lag, Z lead, and here is the P lag, and this value is the P lead. And this K is the K that we obtained from here. Or if you put it as a this equation is also correct. Betul. Okay. Any question? No question. Ada soalan, Ashraf? Tak ada. Ya. Ada siapa nak tanya?
Clear.
Clear. Okay, good. Okay, so we try to do one more exercise. So for a unity feedback system, a forward path transfer function is given by this equation. So design a compensator for the system to operate with 20% overshoot. Peak time 0.15 second from the uncompensated system, and 20-fold improvement of steady state error for step input of uncompensated system. So given dominant pole for uncompensated at minus 2.1 plus J 4.2. Okay, so the name of the compensator is not given. So you need to decide what type of compensator that is suitable for the design requirement state in this question. So if we look at the design statement, to operate with 20% overshoot, peak time 0.15 second. So that actually this value is about the transient values. So that's mean we want to improve the transient response. Okay, so from this statement is the lead compensator ataupun PD from this statement. So we can use the lead compensator or the PD controller. And then in our design requirement, it mentioned about 20-fold improvement of steady state error. Okay, so for the improvement steady state error, so we have lag and PI. But for the PI controller, so we will improve the ESS equal to 0. But for our design requirement, so we just want to improve 20-fold improvement of the steady state error. So the most suitable controller that we need to choose is the lag So because for the steady state improvement is the lead compensator, so the partner for the lead compensator must be lead. So we cannot choose PD lead. So for the combination, active compensator must be with active compensator. Passive compensator must be with the passive compensator. So that's why for this statement or this problem, so the most suitable compensator or controller is the lead controller or lead controller. Okay, so we already choose the suitable, the most suitable controller, lead controller. Okay, so for the lead controller, so we already learned. So first we will design the lead compensator. Okay, so after that we design the lead compensator. Okay, so to design the lead compensator, so first, since in this question, the location of Z lead, P lead, Z lead or P lead is not given, so you need to choose it by yourself. Okay, so for the lead compensator, so the transfer function for the lead compensator is given by G lead equal to K S plus Z lead over S plus Z lead. Okay, basically we choose the Z lead and we choose the Z lead same coordinate with one of the posts from the system. The reason because we want to reduce the time to evaluate or to calculate. Okay, so for this exercise, so I choose Z lead at -1. -1. So we can find the zero pole location at -1 at here. Okay. Okay. So next, so after we choose the Z lead, so for this case, I choose Z lead equal to equal to 1. Satu sama dengan satu ataupun the statement at -1. Okay. Z lead equal to 1 or Z lead choose at -1. Okay, so remember again to design the lead and the PD controller. So we need first to know the ST compensator or ST new. So we need to find the ST compensator or ST new. So the general formula is given by minus zeta omega n plus J omega D. Okay, in the question, the information given is the location of ST uncompensated, minus 2.1 plus J 4.2. And the design statement here, it mentioned about peak time, 0.15 second from the uncompensated system. So when we translate or when we put it into the mathematical equation, so the value of TP that we want to design our desired TP or TP compensated is equal to TP uncompensated minus 0.15. Okay, so this is the statement, the meaning of the statement. Peak time, 0.15 second from the uncompensated system. So TP compensated equal to TP uncompensated minus 0.5. So this is our design requirement. Okay, so for the TP, so since our design requirement is based on the TP value, so that's mean we will use the TP formula. So if you remember, the TP formula is given by TP is equal to pi over omega D. Okay, so that's why from here, so we can evaluate the value of zeta. And then given is the ST uncompensated. ST uncompensated. So for the general formula of ST as uncompensated is given by minus zeta omega n plus j omega d. So from here, so we can calculate before this, our design requirement is the TS, settling time. But for this example, our design requirement is on the TP, peak time. So we will apply the formula, or we need to find the TP uncompensated, pi over omega d. So omega d is equal to 4.2. So we will obtain 0.75 second. So after that, we find the TP compensator or TP new based on the design statement or design objective. So 0.75 minus 0.15, so we obtain 0.6 second. Okay, so from the TP compensated, so we go back to find the ST compensated. ST compensated, which is we need to find the zeta omega n and the value of omega d. So since that we have the value of TP compensated, so we can evaluate the value of omega d. And then we evaluate the value of omega n. We can evaluate the value of omega n since that we have the value of omega d and also the value of zeta from the percentage of overshoot. And lastly, we need to find the zeta omega n. So zeta, and the value of omega n that we already calculate at here. So dapat 2.67. So therefore, the ST compensator is given by this value lah, minus 2.76 zeta omega n plus j omega d. So which one the value of omega d? So our value of omega d should be, saya salah dekat sini. Sepatutnya 5, nanti saya betulkan. Should be the value of omega d. So my mistake. So actually the value here must be the value of omega d should be 5.24. Ada salah kat sini because I put the value of omega n. Sepatutnya adalah value of omega d which is 5.24. Okay, so minus 2.67 plus j 5.24. Then we evaluate the angle. So since that because I put the wrong value at here, so actually the value of theta 1, theta 2 and the value of theta p lead is also wrong. So should be 5.24. So nanti awak boleh kira lagi sekali lah. So I will upload the corrected notes later. Okay. So you can evaluate the theta p lead. And lastly, we can design the location of the p lead. And then we calculate the value of k lead. So please include the 0 from the p lead. Okay. So the answer is k equal to 380. So this is the G lead, our G lead. Okay, next we will design the LED controller. So for the LED controller, so we choose P LED at 0.1. Ini pun ada typing error. So I choose my 0 is at minus 0.1. So that's why for the transfer function, so it become as a S plus 0.1. Okay, since in the question, it mentioned about the step input. Dekat sini. The step input. So for the static error constant, so we will use the KP formula. KP new over KP lead equal to Z lead over P lead. First, we need to find the KP lead. Okay, so to find the KP lead, so we write this formula. Nampak dekat sini, so I include the P lead at here. So Z lead already cancelled with the post from the system. So I just write here the value of P lead. And then we replace the value of gain K that we already obtained from here, 380. And we obtain the value of KP. Typing error KP lead. Okay. Next, we need to find the KP new. So how to find the KP new based on the design requirement. So please remember to find the KP new. We always refer to the design requirement. So 20-fold improvement of the steady state error for step input of the uncompensated system. So that's why we will write the mathematical equation as ESS new equal to ESS old divided by 20. And all here is referred to the uncompensated system since that the statement here is uncompensated system. So that's why ESS all here is referred to the uncompensated system. So we need to find first the ESS all or ESS uncompensated. So to find the ESS uncompensated, so the formula is given by 1/1 plus KP. So we need to find first the value of KP. So KP equation is given by this formula. So please remember to include the value of K. So that's why I find first the K uncompensated. Nampak dekat sini. So only from the system, and ST here is the ST uncompensated. Okay, so we can obtain the KP uncompensated, and then we evaluate the ESS all. So from the value of ESS all based on our design requirement, we can evaluate the ESS new. And then using the formula, we can evaluate the KP new. And then apply again the formula, this formula KP new over KP lead equal to Z lead over P lead. So we can obtain the Z lead. And lastly for the K, so we just assume that K for the lead lead is same with the K of the lead compensator. So which value of the K lead compensator is here? 380. Okay, this is the value for the K lead. So you just put 380 S plus 0.483 Z lag, and then we have Z lead, and here is the P lag and P lead. So we already designed the lead compensator for this question. Okay, so that's all for the lead. Ataupun ni kalau kita calculate. So you can see that the value is almost same, 388, 380. So for your final exam, so no need to calculate the K lead. So you just use this statement. We assume that K lead compensator same with K of the lead compensator. So no need to evaluate the value of K and K. Okay, so that's all. So the next slide is the summary of the controller that we already learned. So you can see the function, the compensator, and also the transfer function and the characteristic. So this is the summary. Okay, PID and lead. Typing error at here, so should be ZPI, and here should be the ZPD. So yang lain sama je lah. So that's all for the lead compensator. So any question? Ada soalan?
So far tak ada, Doktor.
So far tak ada Okay, thanks. Kita break 5 minit boleh? Kelas kita
Boleh.
pukul 11 kan? Saya break 5 minit untuk kita sambung untuk Ziegler Nichols. Sebab awak tak nak kelas hari Rabu kan, hari Rabu kita dah tak ada kelas. So we need to finish one more subtopic Ziegler Nichols. So we will start at 9:55 Boleh Jangan left tau.
Kan doktor, boleh.
Boleh doktor.
Okay, thanks. Okay. Let's continue. Okay, so for our last topic in chapter 1, so we will learn about the Ziegler Nichols techniques. So for your information, so for Ziegler Nichols technique, so we will have a question on assignment and also one question for your final exam. So for the contents, so I put again the contents of chapter 1. So we already learned about the introduction. We already learned about how to design a controller, PIPD, PID, let lead, and let lead. And the last topic from this chapter is the Ziegler-Nichols technique. Okay, for the Ziegler-Nichols techniques, so actually we will use this technique. So before this, we learn all this type of the controller using the root locus technique. So Ziegler-Nichols is the different techniques that we use to design the PID controller. PID controller, which is a proportional, integral, and derivative. Okay, so if you remember, so from the root locus technique, RL technique is the root locus. So the transfer function of the PID controller is given by this equation. So that's mean we need to find the added location of ZPI, ZPD, and also the value of gain K, so we can obtain the PID controller. Actually, there is others way to design the PID controller. So this method that we will learn today is the Ziegler-Nichols tuning method, and the transfer function for Ziegler-Nichols tuning method is given by this equation: Kp in the bracket 1 plus 1 over TIS plus TDS, close the bracket. So this is the general formula for the PID controller using the Ziegler-Nichols technique. Okay, so we do some revision for the PID controller using the standard form or using the root locus method. So the block diagram is given by this block diagram. So the GPID is given by this equation. And we also learn the parallel form. In parallel form, or basically um, we put it as kita kata dia in real implementation. Real implementation. So the PID controller is given by this block diagram, parallel in parallel form. So we have here K1, KP, KI, K2 over S, and KD. Derivative K3S. So the transfer function is given by this equation. And we also learn the relationship between the parallel form and the standard form using the root locus method. So we find out the relationship between the K3, KD, K1, and also the K3. So basically, we also can find can also find the relationship between the parallel form. Here, this equation is from the parallel form or the real implementation, and here is from the Ziegler-Nichols. Okay. Okay, so we can find from here we can conclude that the value of K1 or Kp for the parallel form or real implementation is actually equal to the value of Kp. And for the K2 is equal to Kp over Ti, and K3 is equal to Kp multiplied with Td. Okay, we expand this equation. So when we expand this equation, so it becomes as a Kp plus Kp over Ti S plus Td Kp multiplied with Tds. So that's why K1 here is equal to the value of Kp. K2 is equal to the value of Kp over Ti, and K3 is equal to the value of Kp multiplied with Td. Okay. Okay. So we only find the relationship between the Ziegler-Nichols and the parallel form, since that parallel form is the form or the value of gain K that we use uh, to do in real implementation. So no need to find the relationship between the GPID controller. But if the question asks you to find the location of ZPI and ZPD, so from this value actually, so you can obtain the location of ZPI and ZPD using this relationship. Okay, so what is the Ziegler-Nichols tuning method? So basically, this technique is introduced by Ziegler and Nichols in 1942. And actually, there is a lot of method, but for our discussion, so we will learn uh, on only two methods for tuning the parameters of PPI and PID controller. So the first method is known as a Ziegler-Nichols first method, or this method is suitable for the open loop tuning. And the second method is the Ziegler-Nichols second method for the closed loop tuning. Okay, first we look on the first method. Okay, basically, the first method is applied to plants with step response. So we apply to the system with a step response of the form displayed in figure 1. So if we look at the output step response in this figure, so the response here looks like as the first order system. So that's why this is known as a first method. Okay, so the macam first order system. And okay, this type of response is typical of the first order system with transportation delay. So we can see here. So we have a delay at here. So after that, the response increase and stable at certain point. Okay, such as the introduced by fluid flow from a tank along a pipeline. So basically, we use this method on the process system. So it is also typical of a plant made up of a series of first order system. The response is characterized by two parameters, the delay time and the time constant. So from here, for the T, so we can determine the value or the T for the delay time at here, start from 0 until here. And then the value of the time constant. The value of the time constant. And then from here, we can find actually we can find all this value, time delay and the time constant, from the drawing of tangent to the step response and its point of inflection, and noting its intersection with the time axis and the steady state value. Okay, so basically, so when we have the first order method, so our response will become like this. So from here, so we can find the tangent, we can draw the tangent line, the tangent line. So how to draw the tangent line? So we draw half, half of the stable system. So we put this point, and then we can draw this line, what we call as the tangent line. And the intersection between this tangent line is the the notation that will measure the delay time. So the delay time from 0 until the crossing of tangent line and the x-axis. Okay, and then we draw the final value here. This is our final value from here. So the cross between the final value and the tangent line is the notation of the time constant. So that's mean we will measure the time constant from here until here. Okay, so this is how we can find the equation, the plant model using this equation. So the plant model is given by K exponential minus SL. L is the delay time. K is the value of final value. K is at here over TS. T is the constant value. S plus 1. Okay. So and then from this value, so when we have all this value, T, value L, and the value of K, we can tuning the Ziegler-Nichols values. Means that we can find the value of Kp, the value of Ti, and the value of Td. Since that the most important or the general equation for the Ziegler-Nichols is given by Kp multiply with 1 over 1 plus 1 over TIS plus TDS. Okay, so that is meant to design the PID using the Ziegler-Nichols. So we need to find the Kp value, we need to find the Ti value, and we need to find the Td value. Kalau before this, using the Ziegler, using the root locus method. So when we want to design the PID controller, so we need to find the ZPI, ZPD, and the value of gain K. So same concept for the Ziegler-Nichols values. So we need to find the Kp, Ti, and Td. But for the Ziegler-Nichols, to find all these value Kp, Ti, and Td, so we will refer to the table, what we call as a ZN open loop tuning rules. So we will refer to this table, Kp, Ti, and Td. And it depends on the type of the controller. So using the Ziegler-Nichols, uh, we can design the P controller. P controller is also known as a K gain controller. K gain controller. PI, and PID. So no PD, so only 3 type of the controller can be use this Ziegler-Nichols method. So P, PI, and PID. So how to find the value of Kp, Ti, and Td? So we need to know first the value of T. T is the time constant from this output response. And then we need to find the L, delay time, and we can obtain the value of Kp, Ti, and Td based on this table. Okay, so we try to use or to design this controller using this exercise. So we have the result, the table that display the result from the open loop test. So you need to suggest the value for parameter of PID controller. So we need to design the PID controller to obtain a quarter amplitude of closed loop response. So the full scale change in temperature measure is 10 degree Farad. And proof your PID that have been designed improving the uncompensated using the MATLAB simulation. So this is the result that we obtain. So we have here time and temperature. So we plot this result into the graph, temperature versus time. Okay, so after we draw this graph, so we find out, so we draw the line of the final value. So we obtain that the final value is about 9.4. And then we draw the tangent line. So you just draw the tangent line at here. So we have here the intersection between the tangent line and the final value. So this, so we not this value. So you draw this line, and then the intersection between the tangent line and the x-axis here. Yeah. So so from here we can see that the L or delay time is start from 0 until this value, and from this value until this value, this is our value of t. Okay, so from here the L is measured about 1.4, and for the t, so t is about 7.8. So you need to minus lah. Kat sini 9 point something minus with 1.8. So we obtain for the t, the value is equal to 7.8. And from this value, we can write, or we can obtain the transfer function of this system using this formula. So just put the value of k 9.4, and we have here the value of L 1.4, and then we have here the value of T 7.8 plus 1. And then we design the PID controller based on this table. Okay, so from this table, we want to design the PID, so we refer to this column or this row. This row for the PID controller. So we need to find the value of TI. So TI is equal to 2L. 2L, so 2 multiply with L. So our L is equal to 1.4. Okay. And then we calculate the value of TD. TD from the table is equal to 0.5 L. So 0.5 multiply with L. And last one, we evaluate the value of Kp from this table. The value of Kp is given by 1.2 multiply with T over L. So just put the value of T and the value of L. Okay, so after we obtain the Ti, Td, and Kp, so refer to the general equation of the PID controller. So we can obtain the PID controller for this system. And then we prove. So this is the proof from the MATLAB simulation. So the red color here is the uncompensated system, and the blue color here is the system with the PID controller. So you can see, so the PID when we apply the PID controller, it can improve the response faster compared to the uncompensated system, and the error is also 0, equal to 0 since that from this statement. So the full scale change in the temperature. So this is the input. The input value is 10 degree Fahrenheit. So we can see for the PI, when we put the PID controller into the system, so the final value will become as a 10 degree Fahrenheit compared to the uncompensated system. So we only obtain 9.4 degree Fahrenheit. So this is the proof. So how PID controller can compensate or can improve the response from the uncompensated system using the Ziegler-Nichols. Okay, so then the second method that we need to learn is the Ziegler-Nichols second method. So the second method targets plants that can be rendered unstable under proportional control. So before this, so for the first method, so we apply two plants or to the system with step response of the form displayed in figure 1. Only the response display look like this figure, so you can use this first method. So that means we can conclude that for the first method, we only can apply for the first order system. So for the second method here, so we target plants or system that can be rendered unstable under proportional control. So that's mean that the plant can be operate on unstable under proportional gain. So proportional controller means that this refer to the K gain controller actually. Okay, so the technique is designed to result in a closed loop system with 25% of overshoot. Okay, so we can see here for this Ziegler-Nichols method. So basically we design the output response with the 25% of overshoot. So this is rarely achieved as Ziegler's and Nichols determine that the adjustment based on the specific plant model. And basically, the step to tuning the PID controller using this second method can be obtained from this step. So the first step, we need to reduce the integrator KR and derivative KD to 0. So that's mean we will operate our system with only the KP values because KI and KD is set to become 0. So our plant operate with only KP. And then you will increase the KP from 0 to a critical value. That's mean the value of KP is equal to KP critical, at which sustained oscillation occur omega C naught. If it does not occur, then another method has to be applied. So that's mean for the Ziegler-Nichols second method. So if you so actually you can tuning your PID controller in hardware or in experimental. So first, so you just reduce the KR and KD to become a 0. And then for the KP, you will increase the value of KP slowly from 0 until you obtain the critical value. So how to know that we already achieved the critical value? So if you remember, kalau you ingat, so if we have the root locus of the system like this, okay. So when we increase the value of KP, gain K, so the location of our closed loop pulse is also changed, right? Increase until one time. So the location is on the imaginary axis. Okay, so if you look the response during our ST location on the imaginary axis, so the output location will become like this. Dia oscillate macam ni. So if you remember, okay, ada kan dalam in our first slide so I already show the output response during if our closed loop pulse is on the imaginary axis. Okay, so this is known as the critical values. So the value of KP that we set here is known as the KP critical. Okay, KP critical. So let's say in your experiment, you increase. So but your response didn't sustain this oscillation, this type of oscillation. So that's mean the Ziegler-Nichols second method technique is not suitable for your system. So you need to use another method to design your PID controller. Ziegler-Nichols only suitable for the system that we can obtain the oscillation part or our pulse will be on the imaginary axis. So that's mean if you have a pure second order system. So for the pure second order system, so the root locus will become like this. Goes to the infinity. So our closed loop pulse didn't cross the imaginary axis for this system. So the Ziegler-Nichols second method is not suitable to be used to design your PID controller. So you need to use either the other method such as the root locus method. Okay. Okay. So when we achieve the value of Kp critical, so we can calculate two values, which is the ultimate gain. So ultimate is very simple. The K ultimate is equal to the Kp critical. And then we can evaluate the T ultimate, the period T ultimate, which is given by this formula 2 pi over omega C naught, since that the general formula of omega is given by 2 pi F. So T ultimate is equal to 2 pi over omega C naught. So omega C naught is actually can obtain at the Kp critical. And the last one, so we can tuning the value of gain Kp, Ti, and Td using this table, different table with the first method. So for the second method, we will use this table. So that's mean if we want to design the PID controller, so we will refer to this row. So for the K controller, this row, and for the PI controller, we will refer to this row to obtain the value of Kp, Ti, and Td. Okay, so before this, so I will mention that Ziegler-Nichols, we assume Ziegler and Nichols assume that the percentage of overshoot is 25%. So why Ziegler and Nichols choose the 25% in a damping ratio or the percentage of overshoot? So basically, this value is determine the acceptable stability in sense of ZN tuning method. Okay, so when maybe for this value is the very suitable value for the stability. So that's why Zn assume that the percentage of overshoot is must be 25%. So 25% means that one of the one quarter, 1/4, approximately 1/4. So if we imagine it into the output response, so we have the transient first. So the amplitude for the first cycle and the second cycle at here is equal to 1/4. So it conclude that this 25% is the stability is acceptable. So that's why the tuning is based on the 25% in the overshoot. Okay, so now we learn how to design this Ziegler-Nichols using the second method or closed loop tuning method. Okay, so we have a system 1/s+1, s+3, s+10. So to design it, so first we reduce the integrated KR and derivative gain K to 0. So we just assume that the value Ti is equal to 0 and Td is equal to 0. And then we increase the value of gain P. So in real implementation in experimental, so you can increase the gain value of Kp, but in theoretical, to find the value of Kp, so we will apply or we will use the concept of roof twist. If you remember, ni you dah belajar kan? Roof twist. So basically, we use the roof twist table to determine the stability, the K for the stability. Okay, so for the theoretical, to find the value of KP critical, so we will apply the roof width techniques. So how to apply the roof width technique? So if you remember, so you need to find first the closed loop transfer function. So that's mean if you have any system, so you need to simplify your system until you obtain a single system like this. So this is the value of TS. Okay, so for this system, okay, since that we set the KP and KD is equal to 0, so we just assume that the controller, our controller is only has is the KP proportional controller or K gain controller. So this is our system. So this is the unity feedback system like this. So you need to find the closed loop transfer function for this system. So if you remember in the first topic, we already learned the fastest way to find the closed loop transfer function. So you just write the forward transfer function. So forward transfer function must be include the KP also. So we have here KP S plus 1, S plus 3, S plus 10. Then we extend the division here. And since that this is the negative feedback, so we just put as sum and write all the numerator values. So for this case, so we only have the KP. Okay, so this is the closed loop transfer function that we obtain from our system. And then you need to solve this equation until you obtain, or you need to expand this equation until you obtain in the polynomial form. So from here, so we have s power of 3 plus 14, s power of 2 plus 43s plus 30 plus kp. Okay, and then we will use this characteristic equation to develop the roof width table. Okay, to develop the roof width table, since that this equation start with s power of 3, so we will develop it as power of 3, as power of 2, as power of 1, as power of 0. Ingat tak? Ingat tak? Kan kita buat ni kan, s power of 3, s power of 2, s power of 1, s power of 0. So the equation that we obtain, the characteristic equation or the denominator equation is s power of 3 plus 14 s power of 2 plus 43s plus 30 plus KP. Okay, so ni so we put in the bracket since that 30 plus KP is actually multiply with s power of 0. S power of 0 is equal to 1 actually. So that's why kita tak letak pun. But we know that this 30 plus KP is actually multiplied with s power of 0. Okay, then we draw another two columns. Two columns. So for the s power of 3, so we take the coefficient that multiply with s power of 3. So the coefficient here is 1. So kita letak 1 for the first row. For the first row here, 1. And then For the S power of 2, the coefficient here is given by 14. So kita letak for the second row, 14. And then for the next one here, 43S. For the 43S, we put it on the first column and the second row here. Kalau ingat, 43. And then the last one, we have the coefficient for S power of 0, 30 plus Kp. So that's mean for the roof width table, we will fill the values for two line or two rows from the characteristic equation or from the denominator equation. So we write based on the denominator equation. We take the coefficient, okay, like this. And for the rest of the row, so you need to calculate. You need to calculate. So if you remember how to calculate, so kita akan ambil macam ni. So we will multiply this one. Kita multiply yang ni dulu Multiply 1, 14 multiply with 43. And then minus. And then baru kita multiply this one. 2. Okay, so you dapat 602 minus 30 plus Kp. And then over, so always over this value, dekat atas dia. Okay? Boleh? Okay, dapat ni. So for the next row here, is the same. So that's mean for this row, so same. Since that when you want to fill this value, so you will do the multiply with this value. So since that there is no value at here, 0, so that's why we obtain 0. Or we didn't put anything in this column or in this cell. Okay. Okay, for the next row, S power of 0's row, so the same concept. So we will multiply this one first. Minus this one. And then we divide with this value. Okay, so actually when you do this operation, so so you will obtain this value same with this value 30 plus Kp. Okay, selalunya kita tak buat lah, so we just copy this value 30 plus Kp for the last row as power of 0. Okay, boleh? So this is the way how to construct the roof width tables. So next, the question asks you to find the Kp critical. So if you remember, so we use the roof width table. Basically, we want to find the K stability for the stability, right? So same concept. So we can find the Kp critical. So we have two equations involve for the value of Kp. So the first equation is 602 minus 30. So dapat 572 minus Kp over 40 greater than 0. So the first equation. The second equation, 30 plus Kp equal to 0. So from here, so we have minus Kp greater than minus 572. Then if you want to change the sign here, negative to positive, you will bring this one to here and this one to here, right? So your equation will become Kp less than 572. Okay, the concept when we bring it at here, so you will obtain Kp. The symbol is not changed, greater than 572. or when we change the location of the KP, so we can write as a KP kecil kan. So this one is also less than 572. Okay, and the other value KP must be greater than 13. So from here, so we can conclude that for the stability, the value of KP must be greater than minus 30, must be less than 572. The KP critical is um, the highest values. So for this case, our value for the KP critical is 572. 572. And then from the 572 here, we can find the omega C naught, omega C naught at the KP critical. So at the KP critical, so we will refer to the S power of 2 rho. So for the power of 2 rho here, so we have here 14 S power of 2 plus 30 plus KP. So we refer to this rho. So 14 S power of 2 plus 30 plus KP. And then we replace the KP critical 572. So you can obtain the value of S. So from this case, so the omega C naught 43 square root 43 radian per second. So after we obtain the value of KP critical and the omega C naught, we compute the value of K ultimate. K ultimate is simple, same with the KP critical. And also the T ultimate is given by 2 pi over omega C naught. So omega C naught we already obtained from here, 43 square root 43. So the answer for the T ultimate is equal to 0.958 second. So after that, we just design our PID controller based on this table. So this table is given. So no need to memorize the table. The table is given. But you need to memorize the value of T ultimate formula. So ni formula yang biasa kan, pi and period. Okay. So we can find the KP, TI, and TD, and then put in the general formula of the PID controller using the Ziegler Nichols. So we already designed our PID controller using the Ziegler Nichols. Okay. Okay, so for the exercise 3 is same exercise, but for this exercise, the question extend your answer. So you need to obtain or you need to design the value of K1, K2, and K3 using the Ziegler-Nichols techniques. Okay, so using the Ziegler-Nichols techniques, so we do all this step. This step, so find the closed loop transfer function first, and then construct the roof width table. From the roof width table, we can obtain the value of Kp critical. So Kp critical is 192. And then we find the omega C naught. So we always refer to the row of S power of 2. So from this row, so our equation become 9 S power of 2 plus 15 plus Kp. And then Kp here replace with the value of Kp critical. So we obtain that the value of omega C naught equal to 23 square root 23 radian per second. And then we compute the K ultimate and T ultimate. So after that, we just use the table to obtain the value of Kp, Ti, and Td. Okay, but the question here, we need to find the value of K1, K2, and K3. So remember, from the previous slide, we already obtained the relationship between the PID from the Ziegler-Nichols. And here is from the parallel form. So parallel form refer to this block diagram. So from here, when we compare, so that means K1 is equal to the value of Kp. the K2 is equal to the value of Kp divided by K1. And the value of K3 is actually equal to the Kp multiplied with Kd. Oh, sorry. Kp ni adalah sama dengan value of Kp. So this one is equal to the value of Kp over the value of Ti. Okay. 0.9, 0.655. And for the K3 or K derivative, it is equal to the value of Kp multiplied with the value of Td. Okay, so here is the value of Ti and the value of Td is here, and here is referred to the value of Kp. So we just put all this value into the equation so we can determine the value of K1, K2, and K3. And then when you simulate, the PID controller that are already designed using the Ziegler Nichols method, so you will obtain the output response will become like this. Okay, so from here, so we can observe that the percentage of overshoot that we obtain here is 15%. But in the concept of the Ziegler Nichols, so the percentage of overshoot must be equal to 25%. Okay, so basically we will retuning, so you can retuning you can reduce the value of Kp until the design requirement is met. Okay, so even though the Ziegler Nichols technique does not provide um, the desired our diet design requirement, but it is the starting point to how to start our controller tuning. So after that, you just can adjust your value of Kp until your design requirement is met. Okay. So exercise 4 is same with the exercise 3. Sama je. So you can go through by yourself. So for this exercise, we need to design the P, PI, and PID controller and then simulate all the compensated response using the MATLAB and compare the response. So from here, so you can see for the P controller is the blue one, PI, and the PID controller. So you can see when we use the P controller, is only P controller. So we can see the output response have the ESS. The ESS is bigger. And then for the PI controller, the ping response here. So we have ESS is equal to 0, but we can see that the transient response is not good. So there is a lot of oscillation. Since that what we already learned, the PI controller only improved the ESS, but didn't improve the transient response. Different from the PID controller. So PID controller is the combination of the PI and derivative. So we can see here for the PD controller, so ESS is equal to 0. And also the transient is also improved. So the TS here is improved compared to the P controller and the PI controller. So from here we can conclude that PID controller give the best response compared to the PI and PI and P controller in terms of transient and the steady state. Okay. So that's all for today. So any question? Ada soalan tak? So dekat dalam nota ni saya ada bagi, so this is the question that have been that have been asked in the final exam. Question 5. So you need to answer this question that you need to use the Ziegler Nichols. So you can go through by yourself. So in this example or in this note, I also give the answer scheme. So you can try by yourself to do and compare with this answer scheme. Okay, so that's all for chapter 1. So any question? Ada soalan tak?
Tak ada. Doktor ada tak contoh-contoh soalan midterm? Boleh tak share nanti ke dalam group?
Soalan midterm?
Macam yang pasir ke?
Soalan
Gitu.
midterm dia tak sama because sometimes for this batch, so we ask for the lead compensator. But for your batch, so your midterm until PID controller. So the exercise that I give to you is actually from the midterm and from the final exam question. So you have exercise 2, right? And after this, I will upload another exercise to help you to give you more practice on midterm exam. Okay.
Okay,
So for the chapter 2, so you need to ask Dr. Hairil for the midterm question. Okay. Okay, boleh? So don't worry. So I will do a revision on this topic since that this topic will be asked in your final exam. So for week 14, so we will have a revision class to focus on the question for your final exam for my topics. Okay? Okay? Nanti
Okay,
saya akan bagi lagi exercise. So when I upload the exercise, so you need to answer. So I will for the Wednesday class. So we have no class, online class, no class. So we will do the offline class. So I will give you exercise and you need to submit for your attendance. So nanti saya akan bagi exercise based on the PID and Ziegler Nichols. Okay. So you need to answer this exercise and submit after semester break. So you have 1 week. 1 week to do this exercise and submit in ULearn. Boleh?
Boleh, Doktor.
Boleh So boleh raya dulu, rayalah 2-3 hari. Lepas tu kena buatlah exercise tu. Okay? Okay, so if you have no questions, so I will stop the class at here.